Hello students, welcome to the chapter Matrices. In this video, I am going to discuss about the elementary operations. Using elementary operations, how to find inverse of the matrix also I am going to discuss. Now first see the elementary operations. Elementary operations, or it is also called as transformations of a matrix. Friends, there are 6 operations on a matrix, 3 of which are due to rows and 3 due to columns. That means we have 3 operations on row wise and 3 operations on column wise, which are known as elementary operations or transformations. Now see the first elementary operation. So the first elementary operation is the interchange of any two rows or any two columns. Okay, in the name you can understand what is the operation. Interchange of any two rows. In a given matrix, how to interchange and what is the symbol we used to interchange any two rows, that I am going to discuss now. The interchange of any two rows, let me say ith and jth row or two columns, is denoted as Ri. This is double arrow mark, and this double arrow mark represents interchange Rj. So Ri interchange Rj. So the meaning of that double arrow mark is interchange, or Ci interchange Cj. This is column wise symbol, which means that we have to interchange ith row and jth row of the matrix, or we have to interchange ith column and jth columns of the matrix. For example, for the matrix -1, 2, 3, 5, 7, 9, -2, 1, 1, the operation R1 interchange R3. If I use this symbol R1 interchange R3, then what you have to do it is operated. So you have to first R3 elements, these are the R3 elements row wise. All these R3 elements you have to write now in the first row, that is -2, 1, 1, and second column we have to write as it is 5, 7, 9, and first column we have to write in third column. That means we interchanged first row and third row elements. So this is the method of operating this operation, interchange of rows. I hope you understood the meaning of interchange of any two rows, and similarly columns. If I say that interchange of two columns means it may be any two columns, you should know how to write the elements. Now see the second operation, the multiplication of the elements of any row or column by non-zero number. So it is also very easy to understand. In the name only it is given, the multiplication of the elements of any row or any column by non-zero number. That means any row, any column we can multiply it by non-zero scalar number. Then how it is denoted and how it is operated, let me discuss. The multiplication of the elements of ith row or jth column by non-zero number k is denoted by Ri. Now see in the row, Ri row is changed. This arrow mark represents here change. Okay, Ri changes to KRI. That means ith row elements are changed by multiplying k number to that row. elements. Or if you are operating column wise, jth column, now it is Cj changes to k into Cj. That means the column jth column elements are changed by multiplying k number, which means that the elements of ith row of the matrix is multiplied by k, or the elements of jth column of the matrix is multiplied by k. For example, for the matrix minus 1 2 3 5 7 9 minus 2 1 1, if I take the operation like r1 changes to 2 times r1, that means what you have to do it now, r1 elements you have to change, or you have to rewrite the matrix by changing, by multiplying 2 to this row elements. The meaning of this arrow mark symbol is changes to is operated. So matrix, now this is the first row elements. These first row elements are now changed by multiplying 2 number. Here you can say that 2r1. So now minus 2, that means first element is multiplied by 2, that become minus 2. Second element, it is 2 into 2 4, and third element is 2 into 3 6. Okay, and remaining row elements you have to keep as it is, because according to this written operation, it is r1 changes to 2 times r1. Only r1 is changed. I hope you understood how this second operation is operated. Now third operation, the addition to the elements of any row or column, the corresponding elements of any other row or column multiplied by non-zero number. So the meaning of this operation is you can change any row elements by adding other row elements with multiplying some scalar to other row. Once again I repeat, you can change any row in the matrix adding with the other row elements with multiplying some constant to other row. So this one symbolically denoted the addition to the elements of ith row or ith column, the corresponding elements of any other row, say jth row or jth column. Now here ith row is taken and ith column is taken, and corresponding with other row, say jth row or jth column multiplied by any zero number k is denoted by ri changes to. That means ith row is changed now, ri elements plus k times rj elements, means you have to operate this now. Now jth row elements are multiplied by k. After multiplying, then ri elements position wise you have to add. That gives this operation. Or if you are operating with a column wise, ci column changes to ci, that means that ith column elements plus k is multiplied to jth column elements. Okay, so this is a operation. Now let me see one example here for the matrix minus 1 2 3 5 7 9 minus 2 1 1. The operation, even you can take negative also, you can add or you can subtract. The subtract means the constant is taken here negative, that is minus 1. Okay, the operation r1 changes to r1 plus 2 times r2. So this is the operation written. So this operation is now operated. The first row elements, the first element you have to take plus, because it is r1 element, plus this 2 constant, and next same position r2 element is taken. Now r2 element is 5 here, this element is multiplied. Okay, so simplifying this one, you will get a minus 1 plus 10 means it is a 9. Minus 1 plus 10 means 9, and this 9 is written in this position. Okay, similarly all elements are operated. Now again first row element, second element, first row second element, it is a 2 plus Next, what we have? 2 multiplication and R2 element. Same position R2 element you have to take here. That is 7. Now simplifying this, you will get 16. And this is 16 you have to write in the second position. Next, last element, first row, third element, that is a 3 plus and 2 multiplication scalar, and R3 R2 elements we have to take, that is R2 element here 9. This element is multiplied now. So operating this, you will get a 21, and this 21 you have to write in the third position. And remaining elements you have to write as it is, a second row and third row, because according to this operation R1 is changing, therefore only R1 is operated. So second row elements and third row elements we have to keep as it is, and this is a method of operating this operation. Remember students, we have 3 operations on row wise and the same operations we have on the column wise, and these are very important operations. I hope you understood these operations. Now let me discuss invertible matrices. Definition of this invertible matrices: a square matrix A, the matrix should be square. A square matrix A of order M is said to be invertible matrix if there exists another matrix B of same order as A such that AB is equal to BA, that is equal to I. Now to say that any square matrix A is invertible, remember students, there exists another matrix. Let me denote that another matrix is B, which is order same as A order. And when you multiply with A matrix, no, AB, or you multiply B into A, the result is identity. Okay, that means AB is equal to BA and that product is equal to I. So then we say that A is a invertible matrix. And remember, this B matrix is called inverse of this A matrix. The matrix B is called inverse matrix of A, and is denoted by A raised to minus 1, or we read this as A inverse. Okay, that instead of B we denote that B as a raised to minus 1, that is a inverse we say. Some important point on invertible matrix: if B is the inverse of A, then A is also inverse of A. So it is a vice versa. We say that if A is a matrix, then B is a inverse, or if B is a matrix, then A is a inverse. Okay. Next, we have one theorem on inverse of a square matrix. Inverse of a square matrix, if it exists, it is a unique. That means if you have any square matrix, for that matrix, if there is a inverse matrix, then that inverse matrix is only one. That is, it is a unique. We don't have more inverse matrices to the given matrix. Always there exists a only one. If it is exist, then only it is only one. And this theorem is known as uniqueness theorem. Okay, let me prove this by contradiction method. So let me first take one square matrix of order M. Let A be any square matrix of order M, and if possible, let me take there are 2 inverses of A. Now to prove that inverse square matrix is unique, let me prove that B and C are same. If I show that B and C are same matrices, then it implies that there is a unique inverse matrix for the given A matrix. Since B is the inverse of A, now because B and C are we taken as a inverses of A, now B is the inverse of A means by the definition AB and BA always it is equal to identity. Take this as equation 1, and C is also taken as an inverse of A. Therefore, A into C is equal to C into A. Its product will be equal to I. Now let me consider, we know that B is equal to BI. You study the properties of multiplication. B matrix can be written as B into identity matrix. Now this can be written as I, means we can replace it by AC by equation 2. Okay. Now by associative law we can interchange the bracket because multiplication holds associative law. Okay, it is a BA into C. Now BA can be written as by equation 1. From equation 1 it is written as identity. So it is I into C. Now we know that I into C, it is C only. Therefore what we got here, B equal to C. So which means that the matrix A has unique inverse. That means we don't have more inverses for the given matrix. There is always only one inverse. If I say that there are more numbers, then they are not different matrices. It is the same matrix only. I hope you understood the meaning of this theorem and method of proving this theorem. Now another theorem. If A and B are invertible matrices of the same order, then AB whole inverse is equal to B inverse into A inverse. That means inverse of product of two matrices always equal to B inverse matrix into A inverse matrix. So this is very important result for inverse of the matrices, inverse of the product. So remember, this is very important theorem. Now let me prove this theorem. That is AB whole inverse is written as, or it is also equal to B inverse into A inverse. Now from the definition of inverse of the matrix, we have, so A matrix and inverse matrix, or inverse matrix into A matrix, always it is equal to identity. Now we have AB whole inverse term. Therefore AB matrix and AB whole inverse matrix, it is equal to identity. Okay, so AB matrix and its inverse matrix, always it is equal to identity by using this definition. Now pre-multiplying both side by A inverse. Now we have a matrix equation. Remember students, whenever we adjust any matrix to this matrix equation, either we have to pre-multiply the terms, that is the left side pre, right side pre. Otherwise we have to multiply post. We cannot adjust the equation as we wish. Like in the real number system, we can write in any manner, left side or right side. We can take it in either pre-term or post-term in any manner. But in case of matrices, if you are adjusting the matrix, either it is a pre of the term left side as well as in the right side, otherwise post of the term left side or in the right side. Okay, now let me pre-multiply both side by A inverse. A inverse into AB whole inverse is equal to A inverse I. See, before the term left side it is written, here also before the term right side of the term is written. So this is the method of adjusting in case of matrix equation. Now using associative law, so we can interchange the bracket. So A inverse into A bracket is taken and B separate. AB whole inverse is equal to, and you know that any matrix into I is same matrix, that is A inverse. Now by definition of inverse, it is identity. Inverse and A, it is equal to identity, and B into AB whole inverse as it is equal to A inverse. Now you know that I into B means it is B. AB whole inverse is equal to A inverse. Now to this equation again multiply B, pre-multiply B inverse. So B inverse into B into AB whole inverse is equal to B inverse into A inverse. Now this B inverse into B, it is a identity matrix, and AB whole inverse as it is equal to B inverse into A inverse. So identity into any matrix, you know that it is a same matrix. Therefore, I into AB whole inverse means it is a AB whole inverse is equal to B inverse into A inverse. Now here we got the result that AB whole inverse is equal to B inverse into A inverse. That is this theorem. I hope you understood proof of this theorem. Now you remember some important point. Let X, comma A and B be matrices of the same order such that X equal to AB. So dear students, now I am going to discuss a very important point. If you operate any operation like row wise or column wise, how it is used or how these operations are operated if you have a matrix equation. So I am going to discuss about that now. Let X, A and B be the matrices of same order such that X equal to AB. That means if you have a matrix equation like this, X equal to AB, in order to apply sequence of elementary row operations on the matrix equation X is equal to AB, that means if you are applying any um, any row operation to this equation, remember students, this is very important, we apply these row operations simultaneously on X matrix. That means left side X matrix we have to apply the operation, any row operation, either first one, second one, third one, any one, left side it is operated, and the same operation in the right side it is operated only for first term, that is A, and on the first matrix A of the product AB, that is on the RHS. That means if to this equation, if we are applying any row operation like interchange or maybe scalar multiplication, that operation left side is operated, but right side it should be first term, that is A. To the A it is operated, B we have to keep as it is. So this is the rule. Okay. Similarly, in order to apply sequence of elementary column operations, this is very important. If I am applying a column operations, it may be column wise operation. On the left side, it is X matrix, it is applied, and but the column operation is operated in the RHS to the second term, that is B. Okay. Similarly, in order to apply sequence of elementary column operations on the matrix equation X is equal to AB, we apply these column operations simultaneously on X. Left side there is only one term, of course it is applied to the X, but right side is very important, and on the second matrix B of the product AB. That means if I am applying column operations to this equation, left side there is only one term, to this only we apply, the same operation is operated to the B matrix. So this is very important rule, remember students. Now let me discuss inverse of a matrix by elementary operations. Means using elementary operations how to find inverse matrix for the given square matrix. To find the inverse of the matrix by elementary row operations, because we have two types, one is row wise and another by column wise. So now using row operations, what are the steps you have to follow to find the or to get the inverse of the matrix? To find the inverse of the matrix by elementary row operations, follow the steps mentioned below. The first one, first write the equation A is equal to I. Suppose if A is a given matrix, remember, then to find the inverse of that A, first write the equations. Suppose you are finding the inverse using row operations. First write the equation A is equal to I, and it is equal, you know that. Okay, it is equivalent. It is a true relation. It is a true equation. A is equal to I. And second step is apply a sequence of row operations on A is equal to I. To this equations continuously we have to apply row operations till we get I is equal to BA. That means this left side matrix A, it should changes to identity matrix. So when we apply row operations, it is operated left side, but right side it is operated on the first matrix, that is I. Then what happens? This I also changes, and till you get I, no, left side. When you get I, then here the some matrix you will get. That is nothing but denoted B. Okay. So like this, it is identity. Okay, I means identity of this. If it is two order like this, if it is three order, more number of elements here. And the third point, the matrix B will be the inverse of A, and this whatever matrix we have, no, B, this is the inverse of A. And this is the method of getting inverse matrix when a square matrix A is given. First write this equation. Suppose you are using row operations, and entire in the solution we use only row operations. Okay, we first write this equation A is equal to I, and continuously we use row operations till this A changes to I. So simultaneously what happens, this I changes to some matrix, then that some matrix is denoted as a B, that is the inverse matrix. Okay, I hope you understood. Suppose you are using column operations to find the inverse of the matrix by elementary column operations. Follow the steps mentioned below. The first step, first write the equation A is equal to AI. Now here you have to consider equation reverse. A is equal to AI. If you are using row means IA. If you are using column means AI. Because when we use a column operation to the equation, right side it is operated on second matrix. That is to this I matrix. So rest second step. Remaining steps are same as the previous one. Apply sequence of column operations on E is equal to AI till we get I is equal to AB. That means when we apply column operation, left side there is only one matrix, to this A only we have to apply. So when you are applying column operations means you should get identity matrix. That means you have to change this A to identity. When you are changing this A to identity, simultaneously this I also changes, because column when we operate, it is operated on the right side second term, that is I. So I also changes. When you get identity here, so then at the same case you will get this B matrix. That is only called as a inverse matrix. Third point, the matrix B will be the inverse of A. In examination for the given for the question, uh, to find the inverse of the matrix using elementary operations, either you can find the inverse matrix using row wise operations or column wise operations, anyone using. Now let me take example. Find the inverse of the matrix 1 2 3 4 by elementary operations. Let A is equal to, first denote the matrix, A is equal to 1 2 3 4. Now I am finding inverse of this matrix using row operations. So as I discussed previously, whenever you are using a row operation, so equation is consider A is equal to IA. Substitute A is equal to A matrix here, right side I matrix 1 0 0 1. See, A is now 2 order, therefore identity is also 2 order. If given matrix A is 3 order, then identity is also 3 order, and this A you have to write as it is. Now let me discuss to convert this given A matrix into identity matrix, what are the points or what are the steps you have to follow? So remember, to convert matrix A into I, follow the steps mentioned below. So this is a matrix A. This first step is this 1 1 position element, you have to make it 1. If already 1 is given, this step is skipped. Once again I repeat, the first step, what is the first step? Means 1 1 position you should get one element. If it is already given 1 means that is skipped. The second step is this position element you have to make it 0. That is 2 1 position you have to make it 0. How to make 0 I will explain in this example. Now remember, first step what we have to follow, second step which position, third step is this position, that is 2 2 position, we have to make it 1, and fourth step is we have to make this 1 2 position 0 element. Next, how to make these position wise elements 1 0 and 1 0 I explained. Now remember, first step is given matrix, first step is 1 1 position, we have to make it 1. If already 1 is there means this step is skipped. That means you have to go for this position element, we have to make it 0. Now what we have in this 2 1 position 3. Now we have to make this 3 0 value. It is very easy to make the 0 value. Listen carefully. Now this element is in the second row, therefore write R2 changes to R2 number, and in this position we have 1 no. This same number if I multiply to this position element, it become a 3. Now to make this 0, it is very simple, 3 minus 3 becomes 0. Therefore what you have to operate here, R2 changes to R2 number minus to this one a 3 is multiplied. Okay, when you multiply same number here, whatever number you have here in this position, the same number you have to multiply to this, because here this position you have 1, so it become equal, then take the subtraction, it becomes 0. I hope you understood. Second row element minus the same number is multiplied to the first row element, and then subtract. You will get this second step, that is a 2 1 position 0. You don't worry about the remaining element, you have to operate to the entire row. Okay, now see here matrix. So first row is not changing, you write it as it is 1 2. Now the first element of R2 is 3, write it first, and what we have next, minus what is the multiplied to R1, 3, and R1 element in the same position what we have in the R1, the same element, it is into 1. So this gives you 0 value. So write this 0 value now in the position. Okay, similarly next element of the R2, that is 4 minus, next what we have 3, and what is R1 position element, it is a 2, substitute here 2. Simplify this, you will get minus 2, and this minus 2 you write it here. Now left side it is operated equal to, now right side also you have to operate in the same way. Matrix, first row is not changing, write it as it is 1 0. Now second row is changed in this manner, that is R2 number, that is a 0, minus, now what is the multiplied to R1, it is a 3, that is a 3 into 1. Here you can see. Simplifying this you will get minus 3, and replace this minus 3. Next element, it is 1 in the R2, minus 3 is multiplied to this 0, so it become 1 only, and write the same number here in the position. and A, it is written as it is. Now this is a second step over that we made this 2 1 position 0. Okay, I hope you understood what we have to do it to make this 2 1 position 0. Very simple. Same number is multiplied to first row and it is taken subtraction. Suppose if you have a 5 here, R2 minus 5 R1, because this position 1 is there. Okay, I hope you understood. Now go for the third step, that is making this position 1. See, why we had to follow this step means, suppose you are converting this 1 1 position 1 number. If you go for this one next element 1, suppose next step you are making this 0 means, then there may be a chances of affecting this positions numbers. That means these numbers may changes when you are making this 0. When you are follow these steps without affecting that changes, you are converting identity. Now third step, making this 2 2 position 1 number. To make this position number 1, remember students, always divide whatever we have in this position number using same number. Once again I repeat, to make this position 2 2 position 1, divide this entire row by the same number. So that is, now it is in the second row. No, second row changes to minus half R2. The number is minus 2. Therefore, this entire row is divided by minus 2. Now, what you will get if you do this operation? So, first row, no changes. Therefore, 1, 2. And second row, 0 divided by minus 2. It is a 0 only. And minus 2 divided by minus 2. Or if minus 2 is multiplied by minus 1 by 2, then it is a 1. So, now here you can see that in this operation, this element is not changing. So therefore we have to follow this step. Next, right side, first row as it is 1 0, and second row is divided by minus 1 by 2, or the elements are multiplied by minus 1 by 2. So it is minus into minus plus. So 3 into 1 by 2 means 3 by 2. And next element is 1 into minus half means it is a minus half, and into A as it is. So next step, that is a fourth step, this 1 2 position we have to make 0 number. This position 1 2 position, so now it is a 2 number, we have to make 0. So this is same as the second step, because in this position we have 1. So take the same number, multiply to this row and subtract, this becomes 0. Now we have this equation. Now what is the operation to make that position 0? R1, because this position element is in now in the first row. Therefore R1 changes to R1 minus 2 times R2. So this is the method of making the identity matrix. So now operating this 1, first number 1, first row 1 it is, minus, then 2. Now R2 number we have to take, it is a 0. So this simplification 1 this element. Now we have a second element 2 minus 2. Next R2 element substitute, it is a 1. So this become value 0. So R1 changed now. Now second row we have to write as it is, that is a 0 1. So here you can see that very easily we got identity. The matrix A is converted into identity. Now see, if you operate this, what you will get, the right side matrix. So what we have, Rn number, that is R1 element 1, matrix 1 minus then 2, then R2 element, that is 3 by 2. So here 2 divided by 2 cancel, 1 minus 3 means it is a minus 2. So substitute this minus 2 position. Now next element, that is 0 number minus 2 into, now R2 element, this is minus half. So here minus into minus plus, and 2 divided by 2 cancel, 0 plus 1 means it is a 1. Now this element you substitute here. Second row as it is, and third row, second row as it is, into A. Now this is identity left side. Now right side, this matrix is denoted by B and A as it is. Now we got the equation like I is equal to BA. So this implies this B matrix only is called as A matrix inverse. That is A inverse matrix. That is equal to minus 2, 1, 3 by 2, minus half. I hope you understood how to find the inverse matrix using row operations. Now using column matrix, you can find the inverse of the matrix for the given. So it is also same only. No changes in the answer. Only thing is the position making that element identity matrix is different. You have to follow different steps. Now this is the steps for row operations. I hope you understood how to find inverse matrix using row operations. And also I hope you understood whatever I discussed in this video. Thank you, students.